For a wide array of substances, when you add energy to that substance as heat, one of two things happens. Either the temperature of the substance increases, or the substance is going to melt or evaporate. On the other hand, if you take energy away from the substance as heat, so instead of being transferred in, you're now transferring energy out. Again, one of two things is going to happen. Either the temperature of the substance will decrease, or the substance will freeze or condense. So what this highlights is that in a wide array of situations, there are two types of processes that occur as energy is exchanged as heat. One, you have an energy transfer that's accompanied by a temperature change. Two, you have an energy transfer that's accompanied by a phase change. And so thinking about these two types of processes gives us two ways that we can keep track of energy transferred as heat. The first of these is what happens when you have an energy transfer that comes with a temperature change. That's a specific heat process. That's what we're going to talk about in this video. The other situation is when you have an energy exchange that's accompanied by a phase change. That's a latent heat process, and we'll talk about that in the next video. So for the moment, let's focus on the specific heat. And so what happens in a specific heat process? The temperature of your substance changes. The phase remains the same. So your temperature changes, but your phase doesn't. If you add energy, your temperature increases. If you remove energy, your temperature decreases. So a specific heat process is relatively straightforward. It's what we tend to think of when energy gets added to a substance as heat. In taking in energy, the temperature of your substance increases. In giving up energy, the temperature of your substance decreases. Well, we can calculate this out. And so here's an equation that says our energy exchanged as heat is equal to C times the temperature change. And so the first thing we want to be explicit about is this is a capital C. And we'll see where that matters in a minute. The second thing is capital C is basically the proportionality constant between how much energy your substance takes in and how large is the temperature increase of your substance. Or on the other hand, it's how much energy does your substance give up and the temperature decrease of your substance. Capital C here is called the heat capacity. If you rearrange this equation, I can write the heat capacity is equal to the energy transferred as heat divided by the temperature change of your system. And so if I want to start by thinking about the units of heat capacity, it's going to have units of energy over units of temperature. And so in SI, this is going to be joules per Kelvin. Now what the heat capacity is it's a measure of how much energy must be transferred to a substance to raise its temperature by 1 unit. Again, that's the proportionality constant. And it depends on two things. One, it depends on how much stuff do you have. What's the amount of your substance? And two, what type of substance is it? Different substances have different thermal properties. Even if you have the same amount of stuff, C will be different for different substances. Well, one of the things that we might be interested in doing, of course, is disentangling these two ideas. So instead of have something that depends on both the amount of stuff and the type of stuff, let me break this apart. And so now I've got the energy transferred into or out of my substance as heat is equal to the mass of my substance times this new C value. And again, let's be explicit, it's a lowercase c multiplied by the temperature change of your substance. What we've done is we've calculated out what's known as the specific heat capacity. Specific is used in this sense to mean we took the heat capacity, Q over delta T, and divided by mass. What specific is often referring to is that you have some property per mass. And in this case, the property we have is simply the heat capacity. So again, I can think about the units of the specific heat capacity, and so that's going to be Q over m delta T, and so that's going to be the units of energy divided by units of mass times temperature change. And so again, in SI, this is going to be joules per kilogram Kelvin. What the specific heat capacity is it's a measure of how much energy must be transferred to 1 unit mass of a substance to raise its temperature by 1 unit. So notice we've split apart the 1 unit mass piece from the heat capacity. So the specific heat capacity now only depends on the type of substance. And so what we'll tend to do is say, oh, if we have this particular type of substance, I can go look up what the specific heat capacity is for that substance. So in terms of thinking about this equation, one thing I can do is simply keep delta T as it's defined, final temperature minus initial temperature. And so in that case, what will happen is that the sign of Q will be determined by the sign of delta T. If the temperature of your substance increases, then T final minus T initial is something positive. Multiply a positive value times positive C. Specific heat value is always positive. Mass is always positive. And so that means that your system had to take energy in as heat in order to have that temperature change. On the other hand, if your temperature decreases, then delta T is negative. Multiply by positive C, positive mass, and again that tells you that your system had to give up energy as heat. So Q being positive means that you added in energy as heat and your temperature increased. If Q is negative, then you removed energy as heat from your system and the temperature of your system decreases. Perfectly valid way to deal with this equation. What we'll see is it may be useful, particularly when we have problems where we have both specific heat and latent heat processes, that it might be useful for us to take care of the signs out front. So here's a situation where what we're going to do is we're going to say, I'm going to determine the sign, because it's usually pretty easy to figure out whether Q should be positive or negative. Once I've taken care of the sign out front, I'm going to multiply positive mass, positive specific heat value, and then the absolute value of the temperature change. So this is defined to be, instead of final minus initial, your hot temperature minus your cold temperature. In problems where we have both specific and latent heat processes, keeping track of the signs out front can be advantageous. The important detail, of course, is it doesn't matter which way you choose to do it as long as you take care of the sign correctly.